Hello, let's solve pips. We've got 1 by Ian, 2 by Rodolfo today. We'll start with the easy puzzle as usual. Let's place some dominoes. Okay, we need 4 of something, including a double, so that'll be 3s here. And then we need 4 different things. So, oh, and then 10 in 2 cells, so that'll be double 5. So we need a 3, 5 here, a 5, 0 here. We put a 3 to finish the 4 and avoid our inequivalence, and then that goes there. Great. Okay, let's try the medium. Ooh, interesting little tidy little compact grid here. We need 16 and 3. So that's 2 5s and a 6s, or 2 6s and a 4. Both of those is possible. Oh, but we also have, each of those is possible. We also have 2 6s and the 12. So that means we can't have 2 6s and the 16. Don't have enough 6s for that. So we have 2 6s and the 12, which I guess have to be these, because we still need at least 1 6 in the 16, so we can't waste any 6s. And then we need, 6, 5, and 4 in the 16, I suppose. No, sorry. We need 6, 5, and 5 is what I meant to say. A 6 and 2 5s. Does that mean we need to put this inside? I'm not sure it does, because we... Oh, no, it does, because otherwise, if the 6, 5 went elsewhere, then we would never be able to get 2 more 5s in there because we don't have a double 5. So the 6, 5 does need to go inside. I don't necessarily know which orientation. What about this 4? Yeah, this 4 is the 4, 1. It can't be the 4, 5, or we'd break the 5 because we only have 1, 0. So that goes there. So now we need, oh, and a 3 goes here and pokes out and can't be anything higher than a 1 or it'll break. So that goes there. We need a 0 here. So the 0 could point up or across, I suppose. Right. If it points across, then this would need to be 4 in a single domino, which we don't have, so this goes up. This could still go in either placement. Actually, I suppose this will keep our options open, so I'll put it that way. We need 2 more in the 5, which can't point across because then we won't have enough to finish the 16, so it points down, which means we need our other 3 in the 6, which means the 9 is 4, 5, and that finishes our 16, and there we go. Great. Okay, let's try the hard. Whoa! Wow, we've got an illustration of raindrops falling on an umbrella. This is new. What on earth is going on here? Okay, we have a 3. How many zeros do we need? How many distinct digits do we have? Because we have 6 different things in here. Do we have all 6? Do we have all 7? Or do we only have 6? We have 0, 1, 2, 3, 4, 5, and 6. Okay. So we can't assume we must put a 0 in here, unfortunately. I was trying to figure out how constrained our zeros are, because we have, what, 5 of them? 1, 2, 3, no, 6. 1, 2, 4, 5. Yeah, we have 6 zeros. So 2 of them go here. Basically, what I was trying to figure out is whether this 3 could have anything other than 1s in it, and it can because we have zeros. So, all right. What is constrained here? This greater than 9 must have, it could be 2 5s, a 5 and a 6, or 2 6s. We don't have a 5 and a 6. So it's either double 5 or double 6. Okay. Oh, no, never mind. I thought I saw something, but I didn't. All right. How do we get started with this? Also the greater than 8. What could that be? The lowest thing that's in it could be a 3, but we don't have a 3, 6, which is what it would need to be. So it can't have a 3. So the greater than 8 and greater than 9 are all 4s, 5s, and 6s. So the greater than 9 could be double 5 or double 6. The greater than 8 could be 4, 5, 5, 5, or 5, 6. So that's 3 dominoes, of which, that's 3 dominoes that we have access to. Oh, no, it's 4. There's a 6, 4 as well. That could be either of them. Okay. So we have 4 candidates for those, of which 2 are used. Then we've got a standalone 2-cell equivalence region, which could be double 0, double 1, double 6. And that's it. Double 6 would be difficult, I guess. I mean, that's not saying very much. It'd be a little bit difficult. I mean, it would just mean, all it means is of our high double dominoes, we'd only have 1 left after filling the greater than 8 and greater than 9, but so what? Okay, what about this 4-cell region? That's either zeros, ones, or sixes. Okay, that can't be sixes, right? Because if this were sixes, then we'd need 2 more sixes. So it'd have to be this, basically, or the reverse, which would be the same. And then, well, yeah, well, maybe this does actually work. Weird. I wasn't expecting this to work. Because then we could put 5, 5, and 5, 4 in there. Those would be exactly correct, which is convenient and suspicious. And then we've used all of our 5s and 6s. But there aren't high totals in the grid, so we don't necessarily need those high digits. Maybe this is correct. No, it's not. Sorry, I missed this 5. We have this 5 that's called for. I'm sorry, I completely blanked on that. Yeah, okay, this is not possible. Sorry about that. I just didn't see that at all. What about the 5? If we do the 5s then, that probably causes the same problem, right? Because then we don't even have enough 5s for this. This is impossible for that to be 5s. Right, so the double is 0, 1, 5s, or 6s, not just 0, 1s, or 6s. But this equivalence region is not 5s. So it is 0s or 1s. Okay, if it's 1s, does that cause a problem? Because then we do have 1s called for elsewhere. How many 1s do we have left? We still have actually quite a few. So maybe that's not a huge problem. 1, 2, 3, 4. Yeah, we still have 5 1s left. Wow. Okay, so we have 3 1s left after that. So we'd have 1 more to play with once we put them in the 2 1 individual cells. Okay, I'm not sure exactly how to tackle this. What about this double 0? Where does it go? It could go here. It can't go here. It could, I guess, go here or here. Okay, that's not helpful. Yeah, I was going to say this could be an arithmetic puzzle, but I don't like the idea of having to do that with the inequivalence region because we'd have to do a silly thing where there'd be 6 different ways it could work depending on which 1 digit we left out of it, which I'm not crazy about doing. Maybe the thing we leave out needs to be a 5 or a 6. No, our 6s are actually not very constrained. Maybe it's difficult to put the double 6 in anywhere. We know we can't put it in here. Do we know we can't put it in here? Did we determine that? I think we did, didn't we? Sorry to have to do this again. This would go here, then we wouldn't have enough 5s left because we've used all our 5s, yeah. So the double 6 can't go in there, which means it can't go anywhere in this equivalence region. It can't go down here, obviously, or connect anywhere around here. Can't go here, or touch that. So it would have to go, so in terms of the umbrella itself, it would, oh no, it can't go in here. Could it go here? Is this possible? This would have to be once. Oh, maybe it is. Oh, darn. Okay. That's annoying. I was thinking maybe it couldn't be anywhere in the umbrella, but it could be exactly there. This is really limiting on our 5s, though, because then we need another 5 here, which could be 5, 4, or 5, 5. But it is difficult to get these in. We'd need, one of these here and one of these here. The 5, we could swap these around a little bit, but, something like that. Again, this could actually work, annoyingly. It's very annoying. Okay, so this double 6 could go in the umbrella if it goes exactly here. And annoyingly, it could also go here, or here, or here. So that wasn't as helpful as I thought it was going to be. What about the double 5? We already know it could go here. What do we have very few of? Not much, because we have quite a few dominoes. We only have 3 2s, but 2s aren't explicitly mentioned really anywhere. Okay, what about this 3-cell 3 region? We could put a double there if we put a 3 here. I mean, that doesn't seem very difficult. We could do something like this. Well, but well, we couldn't actually do that because then we'd need a 5, 0, which we don't have. We can't put a 0 there. 1, this would have to be then a 6, 0, which we don't have. Okay, I guess this isn't possible maybe then. I guess that, yeah, this is actually not possible. Okay, well, wasn't expecting to learn that, but it's true. What about the double 1? We then would have to put a third 1 here. Would that be difficult? We can't put a 1, 6 because then we'd need a 6. No, we need a... Oh, no, we could because we could put a 1, 0 there, which does work annoyingly. Okay, that's a shame. Just trying to think if there's any reason that this doesn't work. Can't think of one offhand. Do we have enough 1s left? We have 2 1s. No, we have 3 1s. Ugh, okay. Never mind. Okay, so we can't disprove this double 1. If we put 3, 0 here, we'd need a 0 here, which couldn't be 0, 0. It could be... Actually, I don't think it could be 0, 4. I think we already determined we can't have a 3, 0 there. 4, 2. We don't have a 5, 0. Wait. That wasn't weird. That was wrong what I just did. That didn't make any sense. Sorry. 0, 0 doesn't work. 0, 4. This would have to be 3, 0, which we don't have. 4, 2. I don't know what that was about. 0, 1. This would have to be a 6, 0, which we don't have. 0, 2. This would have to be a 5, 0, which we have. Okay, so it can't be 3, 0. Maybe it does have to be the 1, 1 then. We still have other possibilities, though. It could still be this 0, 1. This would have to be a 2. Could it be 2, 0? No. Could it be 2, 1? No. Could it be 2, 3? I don't... Oh, no. Oh, yeah. Oh, yeah, it could. It could be... Oh, ugh. Okay, it could be this. Okay, what a shame. So that works as well. So we do have more than one possibility, unfortunately. And then... Anyway. Okay. Well, that was a bit of a waste. How on earth does this work? Do I have to just start trying things? Are there things that are particularly difficult to do? I don't know. I mean, this greater than 9 is double 5 or double 6. Is one of those trickier than the other for some reason? Double 5 starts cutting down on available 5s. I guess that is constrained. If that's there, then we only have one 5 left, which must go in this 5, but it could go either down or across. This would be, I guess, more difficult, because this would have to be exactly 1, 4, which unfortunately we do have. So this is two suppositions on top of one another, which is bad. It's not a good way to operate, really. So this is not difficult to achieve, even though it's constrained. It's not constrained enough to be difficult. What if it were... Oh, right, it could also be 6, 4. I forgot about that. I don't think that's difficult at all. Okay, what about this double thing over here? I forget how much I've played around with this. If this is double 0... Oh, does that use all of our zeros? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. It does use all of our zeros. So we'd have to have them all sort of pointing out. I'm not saying they're these. I just mean in general, they'd have to all be pointing out willy-nilly like this. I mean, that's not intrinsically very difficult because they're all going to be different no matter what, so they're not going to break the inequivalence region. I don't think this is going to end. This isn't going to end up. Well, maybe it could end up being 6 actually. Yeah, in theory, it could be something like this. But this was a totally random disposition of zeros. I guess the only one that matters is the one that points down into the 7, actually. The other ones are all going to end up being the same. So it actually doesn't matter. So let's maybe look at those. Let's see if we can make this difficult. So 0, 1 seems to work. 0, 3, I've probably already looked at this from the other direction. How long has it been? Oh, it's been so long. So this would be a 4 pointing into that. That doesn't look very hard to achieve. Okay, I don't know if this is even worthwhile. Let's look at the ones. Is this difficult? We then again would need a bunch of ones all pointing out. I'm not suggesting this is correct. I'm just seeing how many ones we end up poking into various places. We need another one down there. We still have another 1 left over. Doesn't seem very difficult because this 3 down here, which would be difficult, we could still, make no big deal really. Although wasn't the 0, 0 actually not possible? I think actually that wasn't possible. But we could still do something like this. Flip that around. There's so many different ways this could be done. And we can't put a 5 here, and we can't put a 6 there. So it is one of those two. It is 0s or 1s. I mean, 0s is more difficult. Maybe I really do have to focus on that. And again, the only other 0 whose placement is specifically important is the one that points down. So maybe I do really have to work through this. So this is the first one in kind of just order of our dominoes available. So all the rest just point up any which way. And that's all of our 0s. No more 0s used for anything. Oh, which means if we have no more 0s used, then that means the 3 must be 3 1s. I forgot about that. It's totally doable. Does it have to be this way? I don't think it does, because we could also put 1 4 here, swap this around to be the 0 3. So I mean, yeah, these things are still quite variable. Then we'd have 2 more 1s being used around, and then we'd still have an extra 1. We have 7 1s. Yeah, we have the maximum quantity of 1s. It feels like it might be this, but I've not proven anything. What about this one pointing down? Oh, that's interesting, actually. In this situation, well, it could be a 6, or it could be a 3. It couldn't be a 2 or 4 because we already have those pointing in. But that depends what else we put elsewhere. So I mean, it's not necessary. But it's interesting that our 1s and 0s are connected to very similar things. 1, 2, 3, and 4. Is that telling me anything important? I guess our 0s are connected to every. No, our 1s are connected to. Oh, we don't have a 1 5. I guess we don't have the maximum 1s. I'm trying to figure out how to use any of this stuff. I guess if we want to get rid of 6s because we don't need very many high digits, I guess we could do something like this. Although this is dangerous in terms of our high counts. No, we can't do that actually because we've put a 4 in there. But we could, again, the problem is we could flip that around. This could be a 0 3. This could be the 0 4. This could be a 1 3. And all is right with the world. 1 2 3 4. So we need 0 5 6 in the middle. It's getting difficult. I mean, this doesn't work, but I've gone down so many different alleyways at this point that I'm not even sure how much it matters that this particular thing doesn't work. Should I try and focus on getting these zeros to work in some way? Should I think through what might be necessary to make that work? It's been so long, this solve. I'm just going to put them back in again in a completely arbitrary order. These can't be 0, 3, and 0, 4 because we need one down there, but I'm just sticking them in for the time being. This is not possible, what I'm doing, but I'm just putting them in. Right, so if that's zeros, then, and those are in the wrong places. But if that's 0, these we do need ones down there, for sure. So it could be something like 1, 3. I'm trying to get back to a point where I can remember exactly where I'm making determinative decisions, where I'm making decisions that are actually important as opposed to arbitrary. Some things are arbitrary, right? Like these two being in the opposite place is arbitrary. Some things are determinative, like what 0 we put down there. So if we put a 0, 4 down there, then this 1 would have to be 1, 6, 1, 4, or 1, 2. We also need another 1 up here. This 1 couldn't be 1, 2, so this would be 1, 4, or 1, 6. Where does the other 1 go? Can't go in greater than 9, can't go in greater than 8. Can't go in equivalence. Can't go in the 4, but it could go in the void, of course. Could go in either the less than 3 or the void. It's just not constraining. I'm obviously missing an important way to think about this. Maybe now having suspected that these zeros, oh, you know what? Yeah. If we figure out that if we decide to assume that the zeros are in the 4-cell equivalence region, we have no zeros left, which means we know the size of the inequivalence region, which is 21 because it includes all the digits from 1 to 6. So you know what? Let's say, assuming the zeros are in the 4-cell equivalence region, let's do arithmetic on the grid. In that assumption, we will also assume the greater than 8 is equal to 9 and greater than 9 is equal to 10, which might not be correct. But we still have a bunch of equivalence regions and voids, which is crazy. But I'm just going to add these up just in case something interesting reveals itself. And I don't know. We'll see. I'm going to pause while I do this just because it's a big grid. One moment. Okay, I can't tell if this is remotely useful. We have 63 in the grid if we assume the greater than and less than are exactly 1 digit off. But that's also not taking into account these double equivalence regions or the voids, obviously. And then in the dominoes, we have 83. So that's a difference of 20. So if all those assumptions are true, and some of them might not be, the greater than regions could be slightly larger in some cases. If that's true, then the voids plus the equivalence regions must add up to 20, which is, not very easy to accomplish. If we assumed one of them were double 6, that's 12, so we still need 8 more. I mean, what if we assumed one of them wasn't 6? Maybe that's a more interesting way to think about it. I don't know. Sorry, I'm missing a useful way to think about this, obviously. Maybe I should just keep plugging away at this world, trying to make this work. I don't know. So what I have right now is based on assuming that this 4-cell region is zeros, and assuming that this one here is 0, 4. It could also be 0, 3, in which case this 1, 3 would become a 1, 4. I think those are the only two ways to make this work, those two arrangements of the 0 down there. And what does that mean? That means there's always a 1 and a 2 in this equivalence region, so we can't have a 1 or a 2 poking into that, I guess. But we could have a 3 or a 4. We could have this 1, 4. Oh, and the other thing we know is that, yeah, as I said before, if the zeros are this way, where they're in the 4-cell region, then this inequivalence region has all the digits 1 to 6 in it, which means it needs a 5 and a 6. Maybe that is worth thinking about. Because we do also need 5s and 6s in various combinations for the greater than 8 and greater than 9, and for this 5 region here. Maybe that is worth thinking about. The 1 could contribute a 6. Could we put a double 5 there? This could be 4, 5. This could be a 10 to maintain our sort of equal bits. 1, 2, 3. We then need a 4, which could be, this could be 2, 4, and this could be 1, 2. Our other 4 would have to then be here. This would have to be a double. This works. Once again, I feel I've learned nothing. Someone will tell me a very reasonable way to have solved this. Certainly wasn't what I did. I really struggle with the fact that sometimes it feels like the best way to solve these is just to sort of try things. I really want to see necessary logical deductions, but, and I'm sure there were some, but it's just often not how these end up getting solved. All right, well, there we go. That was the pips. That was the hard pips. Back tomorrow. Bye for now.